So we'll continue the discussion about the material selection in mechanical design, and last week we focused on multi-constraint optimization, and that's the minimum that I will expect from you in the project. Okay. Now after that I started talking about multi-objective optimization as well, and that's also quite important. Hopefully, once you go through the case studies, these things will become even more clear. So, in case I believe I came up. Okay, so basically, I introduced the notion of the penalty function. I introduced the concepts of trade-off surfaces, and I talked about this constant alpha, which was the exchange constant, and that allows you to basically uh, compare different options relative to the different objectives at hand. Okay, so that's where we ended the discussion then with this particular example of the bicycle, right? And I said that by changing the slopes, we can basically look into the rationale of our choice of change of material based on these different objectives. Okay. Even in the case studies that I upload, what you'll see is that when having data being presented in the form of these graphs allows you to quickly do a lot of what if analysis. Okay, and I'll mention there, even for a simple case of single objective, how just changing some of the constraints can make a big difference. And you need to think about it, that the things that you call constraints are not necessarily always unique. They are, of course, are a result of somebody's judgment. So let's now look into this discussion of alpha from a different examples point of view. Okay, so when we are talking about transport systems, the cost always consists of two components. One is basically your cost related to the initial cost, meaning in terms of making the material, making the product, so the material that is involved, so it's related to that. Okay, that cost is something that you can get directly from CES. But there is also always a cost associated with the mass of the object itself. Okay, and that cost basically relates to the fuel cost, because the heavier an object is, the more fuel you need to move the same object, and therefore the life cost must be considered when we are dealing with the transport systems. And we can write and therefore we basically have to satisfy both these objectives essentially, and we can define the exchange constant between these two objectives in the same way as I showed in the earlier example, by defining the penalty function z is equal to c plus alpha m. Now, in these cases, I can give you some numbers. Now, obviously, these numbers are based on a lot of what if analysis using these kind of charts. So it's not like, there is a formula that in which I'll plug in the numbers and it will give me output as alpha. Rather, it's based on looking at those charts in a rational manner, and then, after discussions, coming to this sort of agreement. And the typical sort of value that you'll have for alpha in terms of dollars per kg for a commercial, so not necessarily commercial, a passenger vehicle, a small vehicle essentially, which is typically made out of steel, is between 3 to 6. Okay, and why it is so? It is because you see, even if you reduce the mass significantly over the life of the vehicle, that remains a smaller basically that remains a smaller contributing factor, because it's not going to change the fuel efficiency drastically. You can have maybe an extra passenger seated, and all of that mass objective that you gained by changing the material would be lost, right? But when you talk about bigger lorries, bigger trucks, then the exchange constant will be slightly higher, because here you will be more concerned about maximizing your payload, okay, and whatever is the payload will be carefully considered, and therefore the exchange constant there will be higher, and you can now start talking about constructions made of aluminum, and even things like GFRP and CFRP feature at this level, and there is there can be some justifications under certain circumstances, uh, not necessarily always from a mass perspective, but can also be because of the strength perspective. Because if, for example, if you're talking about a pressure vessel, right, that is used for transportation of large quantities of gases at higher pressures, then you may want to also maximize the strength at the same time. Now, when we go for an exchange constant of 100 to 600, this is where the choices really change in terms of the material, and now we are talking about more exotic materials like specialized aluminum alloys as well as composites, and that's basically now the motivation why you see that commercial airliners like Boeing as well as Airbus, they are switching to composites for majority of the components within the aircraft, because the exchange constant between the cost and the mass is such that investing more on the costly material is justified because of that exchange constant, right? So it's all about that justification. Um, and then if you're talking about fighter jets, it's more about performance, and then agility and the ability to travel at that high speed. So again, cost is less important factor to consider, and therefore the exchange constant can be higher and higher, right? At each stage, as the exchange constant is increasing, we are basically saying that reducing mass is more and more and more and more important as compared to just focusing on the cost. And that's why when we talk about the space shuttle, because you simply can't get into orbit if you don't have sufficiently lower mass, and so that's why the exchange constant there can be very, very high. So once we do some more case study examples, these points will become more clear. I'm sure there will be some questions in your mind right now. If you want, you can ask questions as well, but like I said, it will become more clear as we move on. Okay, if there are no questions, I can move forward. So the second thing which I mentioned in my earlier slide was that how do we actually apply this concept of exchange constant on CES? And this basically, what you have to consider is that the penalty function itself is a linear line, okay? So that will, you can plot that on CES, but if you plot that on a graph which is in log scale, then it's not the right approach. So an easier approach is that you simply go back into the CES and convert the graphs first into the linear plots. Once you have the graphs in the linear plot, you use the same index function that is available in CES to plot the line, and with a particular slope -1 over alpha, and then you convert the graph back into the logarithmic scale, where the line will now appear as a curve, and the lowest point on this curve will basically be on your trade-off surface, and therefore it will give you your required material options. So some of these points I'm sure will become more clear in the case study. So next, we have the minimum mass and cost for member. This is an example, right? So example of two objective log chart in CES. So you can see the plot that I have plotted over here. The M1, the material index 1, is representing an objective related to reducing the cost. So that's why the material index is price into density over Young's modulus. So basically, in this case, you can see that the constraint is on Young's modulus, right? Whereas the objective is to reduce cost. And this is an axial member, right? So this thing is coming directly from from the discussion that we had earlier about deriving the material index for, let's say, mass. Yeah. So I've actually explained this in my video as well, but I can just quickly explain this here again. So think about it. The material index to reduce the mass was density over Young's modulus when the stiffness was the constraint, right? Now, mass itself, if you multiply that with, um, sorry, let me put it this way, that if you're thinking about the cost of an object, because eventually all the design dimensions will be fixed, right? So to compare different objects, it's often useful to compare the cost of the material per unit volume, right? Now, if you have the price given to you as cost per unit mass, all you have to do it is multiply that cost per unit mass with the mass to get the cost per unit volume, right? So with that logic, any index which you derive over here for reduction of the mass can be used as a material index for reduction of cost by simply multiplying this with the cost per kg, right? In, for example, dollars per kilogram. So that's why in this chart over here, you can see that the material index, when you're putting that as a function of cost for the stiffness constraint, becomes price into density over Young's modulus. Okay, I have explained this a bit more in the lab demo video as well. So please go back and have a look at that as well. Now the second constraint over here is between is basically, again, the constraint is still on Young's modulus, right? But the objective is to reduce mass. So this material index is exactly same as the one that I was showing you previously. So now if you have to have these two objectives, and now you are trying to find the best material for them, you need to define the penalty between the mass and the cost. Okay, so this basically is your both of these have been plotted in a minimization format. So keep this in mind right now. That means that the materials which are on this corner are basically your potential good materials. The other materials will, of course, not be optimal with regards to both the price as well as the cost. These materials over here are optimal with regards to price, are best regards to price, but they are still not best necessarily regarding to regarding the mass, right? So basically, this will then define your trade-off surface in this case. Okay. Keep this in mind that to keep the example simple, I have not introduced any constraints yet, because a lot of materials will be eliminated because of those constraints, but I'm just showing you the general procedure rather than a specific example. In the lab tutorial, when I do this, I will also be applying the constraints at especially in the second lab tutorial, third lab tutorial, which I have labeled as scenario 2. That's where I will be explaining a lot of how to then also apply the constraints. So now when we look into this trade-off surface, the materials which are near this trade-off surface will be our optimal. So we can now define our, we can now convert our graph from logarithmic to linear scale, right? So previously, sorry, my bad, zoom, yeah. So previously this graph was at a logarithmic scale. When you click on the CES and change the properties of both axes, you can convert it into a linear scale. But on a linear scale, of course, because like I told you, some of the properties are vary so much in terms of their scale, therefore the graph appears very skewed. So now at this stage, you will have to put your exchange constant line with the given slope equal to -1 over alpha. So you'll use the index function that I have used previously as well to plot the index lines, but this time the slope will be -1 over alpha, and alpha will be based on your judgment of the domain in which you are trying to operate. Okay, then you'll just simply put that line anywhere. Okay, but once you have that line, then what you will do is you will reconvert your graph. So right now I have put it here near the end because I know, of course, this is a minimization format, so I should be towards this end. But then I will need to reconvert the graph back into the logarithmic scale, okay? And this is then what you will get in terms of your choices. And you can see based on my particular exchange constant, it's basically as I pull it down, the materials that are over here will be basically your better choice. Once, of course, I put the constraints in, my material selection will become more logical, because obviously I would have eliminated my obviously wrong choices. Okay, so we'll discuss this hopefully more later as well. But even today, I want to share a quick case study. Okay, so this case study I'm not actually going to do on the CES because in the lecture session. Rather, I'll just go through the process, and then there is a different case study that I have that you will be doing in the lab section. And for that, I will go through each of the steps on the CES, as well as the calculations. I will show you the formulas for them, and we'll do that together. But for now, just let's look into the case study from the point of view of understanding the process. Right. So what this case study is about? This case study is about the common bumpers of your automobile, right? And we are talking about a typical commuter automobile. So we're not talking about a very large vehicle right now, but later on we'll see how those choices can actually affect as well. So first thing is to do the translation, isn't it? And when we do the translation, we have to define the function in the mathematical manner. So in this case, I'm saying that the function of a car bumper is to absorb the impact, right? And transmit load to energy absorbing units or supports within the vehicle, isn't it? So basically, when we say absorb impact, what do actually we mean? We actually mean is that maximizing essentially your energy, strain energy, basically, the ability to store the strain energy elastically within that object, right? And if you think about the impact topic, how do we achieve that? Is by increasing the delta static, right? So that's one of the things. The second thing is to transmit this load to energy absorbing units or support. For that, basically, you are saying that your F needs to be then transmitted back to the other members. But in the process, the bumper itself should not break. Okay. Now, this is a fairly complicated example, but for the purpose of this demo, we'll only look into certain aspects and not consider every aspect of it. Okay. So right now, I'm just looking at it from the point of view of two objectives. One is to minimize mass, and the other one is to minimize the material cost. Okay, because we don't want the bumper to make the car unnecessarily heavy, right? Because again, that's not the primary function. It's mainly contributing towards safety, right? And we also don't want the bumper to be so expensive, because that's the first thing that will get damaged in an accident. So most likely you just want to be able to replace that very, very quickly, rather than worrying about how much costly it will be to repair, right? Because that's the first component that will be sacrificed in case of a impact. So you're trying to minimize cost. There can be other objectives as well. Like I said, you can think about the energy absorption or the fracture toughness as well in these contexts. But to keep the example simple, and in these slides, those objectives are not considered. Okay. Now, in terms of the criteria, the mass per unit of the bending strength is something that we are trying to essentially optimize, right? So basically, we are saying that yes, we want to reduce the mass, but we do not want to compromise on the flexural strength of it. Okay. Secondly, we want the cost per unit of the bending strength to be optimized as well. Based on this, you've got these two material indices, right? And the first material is density over yield strength raised to power 2 by 3. And if you remember, in last week, when I did the derivations, I also showed you the derivation of this particular material index, right? So that has already been covered in your lecture session. And I also showed you in the demo video in CES that even if you don't know these material indices, you can use the performance index finder tool in level 3 databases and above to basically just simply find the required material index directly from the software. Anyways, in this case, we now know that the one of the material index is density divided by yield strength raised to power 2 by 3. And in terms of cost, that material index becomes cost into density divided by yield strength raised to power 2 by 3. Now, in terms of, because now we have got these two objectives, but keep this in mind, to keep things simple, we are looking at it from the point of view of a single constraint right now, right? So this constraint is 1, objectives are 2. Now we define the penalty function between these two objectives, again in the same format as I explained earlier. So z is equal to c plus alpha m. In this case, when you rewrite the equation for the cost and mass, this therefore becomes, you can just simply take the material index rho over sigma yield raised to power 2 by 3 common, okay? Keep this in mind, it's not necessary that you take these out common, but in many cases, if the objectives have the same form, you may be able to take some of the material properties as a common factor. So now you have got the Cm plus alpha as defining your penalty equation. So rho over sigma yield 2 by 3 into Cm plus alpha. So that's your defining your penalty function. Okay. How can now we apply this penalty function in CES? So basically, you will be, you have several ways, okay? One possible way, which is different from what I was just discussing in the slides earlier, is that you actually simply plot this penalty function, right? Because if you plot this penalty function, because in this case, you were able to, take this out as common term, you can simply plot the penalty function and look into the material options available to you and then compare them for various values of alpha, okay? So this is something that you can do. So we can go into the advanced feature of the CES. There we can type the function, which is density divided by yield strength raised to power 2 by 3, which means is 0.666, into price plus, now this will be replacing alpha, right? So right now I have arbitrarily put 10 as my alpha, but later on I will compare different values of alpha to see how that changes my material selection. Okay, so with this we can now plot the first graph. So when you plot this graph, you will end up with this type of a material selection, okay? So with this, you can see here, now obviously this has the subset of the materials that that is being considered in the slides has already been reduced. So it's not the full 3,000 or 4,000 materials, rather we have already reduced the subset of the materials to make it easy to compare those options. And maybe, for example, certain limits would have already been prescribed, like fracture toughness. There should be a minimum benchmark. You don't want very brittle materials to appear in this selection. Manufacturability into that shape, so moldability, that can also be applied using the tree control in CES. So those options would have already been applied at this stage. So now the graph that I'm showing you basically has this value, not 10, rather it is 1, okay? So when the value of the exchange constant is 1, the materials that are showing here at the bottom are the ones basically that minimize this penalty function, right? Isn't it? And if you minimize the penalty function, then that means that those are the best candidates. So in this case, the best candidates are, all of them are essentially steels, right? So you have some high carbon steels, some low alloy steels, some medium carbon steels. They are quite close to each other in this. And then after that, you have some plastics as well if you are able to compromise a bit on this penalty function, and things like PET, etc., appear in this selection windows as well. Okay, yes.
What's the x-axis?
So the x-axis is basically nothing, because it's right now just plotting on the y-axis and comparing all these with regards to this. So x-axis is just basically the materials have been simply ordered. Yeah, they have been spread out. Yeah. So y-axis is basically what is telling you the actual whether it is minimum or maximum, because we are just plotting it on one axis. So it's like one of those bar charts that you plot in Excel, right? Okay. So this you can think about. So if you think about it, in early days of automobiles, you had a lot of these bumpers made out of steel, right? So that would be their justification. In their sense, the exchange cost was very low, right? So they were focusing more on the price, and weight reduction was really not a big issue. You had those big cars, nobody was bothered about the weight at that time too much, right? So if you change that exchange constant, and if you make it 10, so now you are kind of reaching the limit of a typical passenger car's alpha, and you are now in the domain where you may be talking about a performance car, right? High performance car, like a sports vehicle, right? So that's now where you're talking about, because now you value reducing your mass significantly, right? And as soon as I change that value of alpha over here to 10, you can see that the minimum options completely change. There are no steels immediately in the far right corner. There are certain type of high carbon steels, okay, because of their very high strength and fracture toughness. They still appear in this side, but really the competition is between some exotic magnesium alloys and between the CFRPs, okay. Now, in this case, basically, the cost will be much higher than previous case, but that's okay for us because we have said that we are able to spend 10 times more than the previous case. So can you see what this is doing? This is allowing you to take that management decision, isn't it? So you are saying, if I'm happy to spend 10 times more on this car, then these are my choices. But you won't do that for an ordinary customer. You'll do that for customers who are willing to pay 10 times more, right? And that can be your performance sports customers or prestige clients who are willing to pay that much for that vehicle, okay? So that would allow you to think about it. So for example, when BMW introduces all carbon fiber bonnets or bumpers, then they have a certain clientage in mind. They're not making that vehicle for their average Joe. Okay, so that's how would come up to this analysis. Then, if you raise it even further to 100 per kilogram, then your CFRPs actually become the obvious choice, and that's why for passenger cars, they may be using it in certain high-end models, but it's not really justified to use it for bumpers as such. There can be other structures in which you can use it, but if you just purely look at it from the point of view of cost and the mass in relationship to the yield strength, then the exchange constant has to be really high to justify the use of CFRPs. But you have other other plastics as well that also feature in this. So this obviously analysis was deliberately kept simple, okay, because I'm doing this in a lecture. So as I said to you, we have to consider other options, other constraints as well. So for example, in this case, to reduce the actual impact force, reducing your Young's modulus can also play a role. So you have to look at this from the point of view of the stiffness constraint as well, isn't it? So that's also important. So ideally, you'll be running this analysis with then multi-constraint and multi-objective, okay? Maybe, first of all, you'll consider what is your primary objective, right? And based on that primary objective, you will carry out a multi-constraint optimization. So then the materials that are the best sort of 10, 20 materials on that based on the primary objective, then you'll do to this sort of multi-objective phase where you can then compare out of those remaining options, okay, and then focus maybe on just one constraint, right? So there's a lot of judgment that needs to be applied when you are using this methodology, It's not like just simply picking a formula and plugging in the numbers. Okay. So let's now see the other way you can see these results as well, right? So the other way you can see these results is by plotting your material indices. Like I said, now this time we are not plotting the penalty function, rather we are plotting the actual material indices. So I'm plotting the price related material index on my x-axis and cost related material index on my y-axis. And in this way, I can now define my trade-off surface, and I can also define my penalty function. Now with that penalty function, I can now keep plotting different values of z, okay, and I can just display them, and with those I see that, you know, with the value. So now this one I would have done using the procedure that I just explained to you. First I would have switched to linear, then on linear I would have used the index line, then I would have moved back to the log, and then I'll get this curve, right? Then if I change that to alpha 10, you see my options change. I'm in a different zone. If I change it to 100, then it even changes further. Okay, so this is how you can compare different options for material selection. Now, I have just a few more closing remarks. So like I said, in the case, I will be uploading this case study for you on the D2L. So part of it is already recorded, and part of it I will be finishing today, and so hopefully I'll make it available to you. So let me just quickly show you the case study that I will be considering. So the first case study will be related to this sort of a rope for a towing cable, right? So it's basically that you can use to tow cars, and this is related to, you know, what we did earlier in impact as well. However, I'm not actually doing the full impact analysis, rather I'm doing it using the static assumption. Okay, but so basically I'll be looking at it from two point of views. Okay, and the first point of view is further subdivided into two parts. So I'm trying to build up, you know, the difficulty level. So in scenario one, I'm saying everything is fixed in terms of the geometry: length, diameter, maximum load, you know, the deflection that it can have, the mass that you can have. Everything is being specified to you as a constraint, and therefore your only free variable will be your material choice. This is the easiest sort of thing to do, and this is what you would normally do only at detail level, right? Not at embodiment level, because at embodiment level you need to have certain free variables. In the first scenario 1A, I don't even have a specific objective there, right? I'm just saying that as long as you specify meet the constraints, you give me the option. In scenario 1B, then I introduce an objective of minimizing the cost, okay? And then I show how that changes your material selection. After that, I do scenario 2, in which is more like at embodiment level. So I basically then tell you that that it's not just that everything is fixed, rather your diameter is fixed, is free. So you can basically keep changing your area and see what the different options are. And that's where then the things will become a bit more complicated, because you have got, you have to look at the objective of minimizing of the cost with regards to both the strength as well as the stiffness constraint simultaneously, and you also have to meet the constraint on the mass. So that's a very interesting problem. So once I've uploaded it and you go into the lab session, please do spend time on it, and hopefully you'll find that useful. Okay, if we are left with some time next week, I may be actually going back, maybe introducing another case study, but I'm not promising that yet, because I don't know how much time we will have, and that will be related to the transmission shaft. And in this case, you can have several objectives. So for example, you can look at it from the point of view of reducing the mass in context of the strength as well as stiffness. and you can also look at it from the point of view of making it more damage tolerant, especially for high-end shafts, like the ones that you use for motorsports application. For other shafts, typically you will only have this as your main objective, and then you'll use this instead of using the strength here will then mean endurance limit rather than the yield strength. Okay, so that will be then the primary difference between these two. Anyways, I'll leave this discussion for later, and hopefully we'll continue this now in our lab session. Thank you very much.